Polynomial functions are usually written like this in general. Now what this means, well, I'll break it down into parts. Each of these A's, each of these purple A's with little numbers next to them, they are just numbers. They just represent numbers, they just represent coefficients. Now each of these coefficients is multiplied times an x. This is just an x to some power. This power is a positive whole number, so it could be, 1, 5, 10, not negative numbers, not fractions, positive whole numbers. But let's say this is x to some power, and then this is also x to some power that is 1 less. So if, for example, say if n was 5, then over here you have x to the 5, fifth power, and then you'd have x to the 5 minus 1, so you'd have x to the 4. So now what this ... means is that we're continuing on in this pattern. So if we have x to the 5 and then x to the 4, then actually next we would have x to the 3, and it just keeps counting down until we get to x to the 2, and then x, which is the same thing as x to the 1, and then there's no x, which is the same thing as x to the 0. So a polynomial function, going back to this x to the 0 because anything to the power 0 is just 1, so you multiply times whatever number it is and it stays the same. So you can see that we start with some number n, some power n, and then we're just counting down by 1 all the way to 0 in the powers. And then each of those x's can have a number multiplied by them. This number, this a, could be positive, it could be negative, it could be a fraction, it could be a decimal. Doesn't really matter what kind of number it is as long as it's a real number. You can't have like I, or you can't have a variable. It has to be an actual number. Now, the reason we put these little subscripts, like a sub n, is just to say that this number, this coefficient, a sub n, whatever it is, it goes with the x to the n. Over here, we have a sub n minus 1. That's just saying that this number goes with the x to the n minus 1. Same all the way down. A sub 2 goes with the x squared. A sub 1 goes with the x, or x to the 1. So I'm going to skip down to this function I wrote down here. And this polynomial function, I just wrote out, as you can see, 5, just a normal number, times x to the power 7. And then from there, you can see 7, 6, 5, 4, 3, 2, 1, 0. I just counted down the powers, and there's one of each powers from 7 down. You can start at any number, but once you start at that number, you have to do every single one down. However, it's important to note that the number that you are multiplying times the x, can be 0. So if it is 0, sorry, that's a little messy, that's a 3, that's a 0, 4, 0, and 2, which is just the coefficient at the end. The constant at the end. If it is 0, we don't usually write them out. There's not a whole lot of point. 0 times anything x could be, it will still be 0, so it just goes away. So right above it, I have rewritten the function the way you would normally see it, which is 5x to the 7th plus 7x to the 6th plus 3x to the 4th. Now, this is just one example of a polynomial. These numbers, again, could be anything, positive, negative, fraction, whatever. And these could have started at a different number. You can theoretically skip numbers because of the 0. Notice we skipped the 5, the 3, and the 1. And we just don't write them, basically. So this is a polynomial. When you're looking for polynomials, what you're generally looking for is number, times x to some power, plus or minus number times x to some power, and then that can just go on and on for a very long time, all the way down, and you should end in some number. Although you don't have to have a number at the end, but you probably do. Okay, a couple names associated with polynomial functions. The first one I'll talk about is degree. We call this n, or we call n the degree. As you can see from up here, n was our highest power. So in our polynomial that we had right here, the highest power we have is 7 here. So we say that n equals 7, or you could say that the degree is 7. Alright, the next one, a sub n, is called the leading coefficient. Now remember, coefficient is just the number in front of a variable. And in this case, the leading coefficient, remember up here, see, is the number that's next to the highest power x. So in our function, the highest power was x to the 7th, and the number that goes with that, the coefficient that goes with that, is 5. So we could say a sub n equals 5, or the leading coefficient is 5. Next we have a sub o, or a naught. This is called the constant term. It is the lone number at the end, if there is one. As you can see from here, a sub o doesn't have an x anymore, because it was just 1. So in our polynomial, the number by itself here is 2. So a sub o is 2, or 2 is the constant term. Just a general note when it comes to polynomials, this is the right way to write it, with the highest power first and then next power, and then you're just putting them in numerical order with highest powers first and then lower and lower powers, and then you end with the constant term. However, if you took each of these things and put them in a different order, it would still be a polynomial, it just wouldn't be a very well written one. If you had this all out of order, you would probably want to rewrite it in order. That's just what people do. Makes it organized, makes it neat. You can see what you're doing, etc. Okay, things that happen with polynomials, trends that sort of tend to happen. The maximum number of real zeros is equal to n. So now the question is, what is a real zero? What does that mean? If you're trying to find zeros, or you're trying to find real zeros, they are the places the function crosses the x-axis. We call them zeros because y is 0. You can see right here, all these dots right here are all places our function, our line here, crosses the x-axis where y is 0. So if, I don't know, say this is -7, and then this is -3, and this is 1/2, and this is 6. I'm just guessing vaguely what those numbers look like. We would say our real zeros are -7, -3, 1/2, and 6. Because they're the places the function crosses the x-axis. In our polynomial, n was 7. Remember, we determined that. It was the highest power. So, what this is really telling us is that it can't cross the x-axis any more than 7 times. At absolute most 7. It could be less, it very likely will be less, but it won't be more than 7. So for this blue drawing that I have here, it only crossed 4 times. So if, say, n had been 4 for this function, whatever this is, you could see that it does actually cross 4 times, but like I said, this is the maximum number, so it might be less than that. The number of places where it crosses could be less, but it won't be more. Oh yeah, and I have this example here. For example, f of x equals x to the 4th plus x minus 1. What is the maximum number of places f of x can cross the x-axis? Well, as we can see, the highest power is 4, and the maximum number of places is n, which is 4, so the answer is 4 for that. Okay, more things that can happen. The maximum number of relative extrema is equal to n minus 1. So in order to know what that means, you have to know what relative extrema is. In short terms, it is a turnaround point. Like you can see here, it was going up, now it's going down. That's a turnaround point. That's a relative extrema. As you can see here, with this arrow, it was going down, now it's going up. Another turnaround point. It will be the highest or lowest point in its little neighborhood nearby on the function. As you can see, like this point, it is higher than everything next to it. It may not be the highest point of the function, like this is probably going to keep going and go up higher, but within its neighborhood, it is the highest, the most extreme point, which is why it's called extrema, and it's relative to its area. That's why we call it relative extrema. Another note, extrema just is the plural of extreme. So what we were trying to find again was the maximum number of relative extrema. So from our polynomial, if you recall, the n was 7, as we have determined several times already. So n minus 1, 7 minus 1 equals 6. So 6 from our polynomial from before is the absolute most number of relative extrema the function can have. The example here is how many possible relative extrema are in the polynomial f of x equals 6x to the 3rd plus x squared. Now remember, you have to start with finding n, the highest power, which is 3, as you can see. And then we want to take n minus 1, so 3 minus 1 is 2. 2 is the most possible relative extrema, or turnaround points, that you can have in this particular given function. Alright, one more thing for this video. Y-intercepts, so places where it crosses the y-axis, happen at the point 0, AO, A sub O. Now, if you recall, see if I can bring it back. A sub O is our constant term, as we said here, and here. It's the lone number at the end. So, we just make the point 0, pull the lone number out at the end from whatever and plug it in there. And then you've got a point, which is the y-intercept. Just as a side note, since this uses the word term tends to mean, this is a very vague definition, but with polynomials, it means a group of letters or numbers in between the pluses or minuses. So like I have here, you have 7x squared letters, numbers, that's a term, and then you have a plus, and then you have another term, and a plus, and then you have another term. So each of those things are each terms. So we call it the constant term. It is a term, and it is constantly the same number. In our polynomial, if you recall from before, the constant term was 2. Therefore, the y-intercept occurs at 0, 2, which is that coordinate pair.